Hi, everybody. Today we are going to move on to investigating acceleration and distance. So we've already done, investigating velocity and distance in time, and now we're moving kind of one step forward into looking at how acceleration works. So let's just jump right into it because these lessons tend to take a little bit longer than I intend on them taking. Okay. So, investigating acceleration and distance. What does this look like? Oops. Physicists define acceleration as any change in the velocity of an object during a time interval. So, whereas before we had the velocity was any change in the displacement of an object during a time interval, now the acceleration is any change in the velocity during a time interval. The change can be an increase in velocity, but just because it says acceleration does not necessarily mean that it has to have an increase in its velocity. It could actually be getting slower as well. So it could be a decrease in its velocity as well. This is also technically an acceleration. We just call it a negative acceleration. You might have heard the term deceleration as well. So the change it could be also doesn't have to necessarily be in a change in the velocity. It could also be a change in the object's direction, or in the direction that that object is moving. So let's first off look at how to graph acceleration because it's a nice visualization of what acceleration actually looks like. So by analyzing graphs of distance versus time, you can determine whether the velocity is zero, constant, or changing. And by changing, I mean accelerating. And you can learn even more about this type of changing behavior if you graph velocity versus time graphs. So I'll show you them side by side, and you'll see the difference between the two of them. So if I put up here side by side, on this side right here, I have a position time graph. So this is like my distance time graph, right? Or displacement time. Okay, and then I have my velocity time graph over here. Now my position time graph is showing a straight sloped line. We saw this in our last notes, right? This just means that an object is moving at a constant velocity in the positive direction, right? For every like 1 second, maybe it's moving, I don't know, 2 meters or something like that. And then we know it's going 2 meters per second. Now, what that means on a velocity time graph is that the velocity is constant, okay? Because if I was showing you here that in every second it was increasing by 2 meters, well, that means that it's going 2 meters per second, right? And if it's going to, oh my goodness, my mouse is not working very well. And if it's going 2 meters per second, well, say this right here was just that, 2 meters per second, that would mean that for any time interval, it is just going 2 meters per second. So it's a straight horizontal line at the specific speed that the object is moving at. Now, what if we graph acceleration? So this is a zero acceleration scenario. So when you graph the velocity versus time of the same object, you get the graph shown in B, a straight flat line. This is telling us what this is telling us. This is just the same graph as the last slide that we looked at. What this is telling us is that the acceleration is constant, and the acceleration is actually zero in this case because the slope of the line would be zero. Right? The slope of this line has no slope. It's completely horizontal, right? And if a line is horizontal, that means that the slope is zero, which means that the acceleration is zero. It's easy to see it mathematically, right? You take your y2 minus your y1. Well, those are actually going to be the same value, right? They're both going to be 2. So 2 minus 2 just gives you 0, which would give you an acceleration. Now, what if we had a positive acceleration? What if we had something speeding up? Now we see some interesting stuff here. Now we see a line that is curved upwards like this, okay? And that means that as time is going on, I'm going to set up 2 points here. I'm going to set up 2 intervals right here. I'm going to try to do very similar right here, okay? as time is going on, what you'll see on the y-axis is if maybe this, let's say this represents 2 seconds. Well, on the y-axis, that means that it covered that much distance in meters. But over here, as my slope is starting to get a little bit more substantial, it's speeding up. And this is also representing 2 seconds. Look at this now. Now the distance covered on my y-axis is larger than it was down here. This distance right here is larger than this distance right here. And that means that we're covering more and more distance as these time intervals are going on. That means that the object is getting faster. So this represents a change in velocity. When you graph the velocity versus time of the same object, you get something that looks extremely similar to what we saw on the last slide. And that's just because it's a constant acceleration. The velocity is increasing at a constant rate. We're not having an acceleration of 1 meter per second squared, then 2 meters per second squared, then 3 meters per second squared. The acceleration itself is actually constant, staying the same. So the slope of the line in graph B is rising up to the right, which indicates a positive slope, meaning that the rise over run will be a positive number, and that means the object is undergoing a positive acceleration, which in other words just means that it's getting faster. What about if an object is getting slower? What is that going to look like? If you said something like this, you're exactly right, okay? Just exactly like this, opposite type of slope. And now the slope is not going up, the slope is going down. So in the distance time graph, the line curves downwards. This indicates that the velocity is covering less distance over every interval of time, right? Let's do this again. Let's try to make these time intervals all equal distance apart. Let's do 5 of them. And then I'm just going to place my points here on the y-axis. And what you'll see is the points will start to get, if I have them over here, what you'll notice is that they'll start to get closer and closer and closer together, right? See that? Pretty easy to see that. So they're getting closer and closer and closer together. If I had another one up here, well, it would be even closer to this one. So what we have is a scenario where it's slowing down. For every second that passes by, it's covering less distance. Now, if we take a look at graph B, it shows a straight line again, which shows that the velocity is changing at a constant rate. So the acceleration is constant. But in this case, if I go right here, I choose 2 points on this, right? I choose a point right here, and I choose a point right here, and I calculate the slope. Well, this right here is x1, y1, right? And this is x2, y2. Well, if I do y2 minus y1, right? Well, that's what I always do on the top, divided by x2 minus x1. This is going to be the same as always, but what's going to be different about this one? y2 is down here, and y1 is up here. So say this is maybe a value of 2, and this is a value of 6. 2 minus 6 is going to give me what? A negative number, right? That's going to be negative. So in this case now, the slope of the line is negative and will be a negative number if I calculate the rise over the run, which indicates an object slowing down, a negative acceleration. So you may have heard the term, like I said before, deceleration. It's not technically the correct scientific term. We like to use the term negative acceleration instead. Because acceleration just means a change in velocity. So it doesn't have to necessarily be Let's take a look. So let's stop looking so much at graphs. Let's take a look at how we do it mathematically. Okay, the definition of acceleration is the change in velocity. We already talked about it over the change in time. It's important to use change in velocity for this calculation. So that's what that little triangle is that we call, it's not a triangle, we call it delta. It's a Greek letter in the Greek alphabet, and it means change in. So the velocity changes, Vf minus Vi. So the final velocity minus what its initial velocity was. So the acceleration is the change in velocity over the change in time. To calculate acceleration, you're always going to need three pieces of information at the very least. You're going to need its initial velocity. We call it the initial velocity. It's how fast it was going at the start. It's beginning velocity. You'll need the end velocity. We call it the final velocity. So how fast it was going at the end. And then you'll need the time interval. So how much time passed during which that change in velocity happened. So those, if you have those three pieces of information, you can find what the acceleration is. So let's do one together. A biologist observed a cheetah reach a velocity of 19 meters per second from a standing start. This is very important because this is telling us that the initial velocity is equal to, if I'm standing there, how fast am I moving? 0. Okay, 0 meters per second. So a standing start, 0 meters per second. It ends up getting to a speed of 19 meters per second in a period of 2 seconds. So what was the cheetah's acceleration? And assume that the cheetah runs. We know that Vi is equal to 0. We know that it gets to a speed of 19. And we know that it did that in 2 seconds. So this is already calculated for us. So we take our formula. A equals delta V over delta T. So Vf minus Vi over delta T. Vf was 19, Vi is 0, and the time interval was 2 seconds. So 19 divided by 2 gives us 9.5 meters per second squared. That's what the cheetah's acceleration was in the positive direction. So almost always we will use, sorry, if I went too fast there, you can follow. Almost always we will use meters per second squared for a unit of acceleration. And this is because we're dividing velocity, which is meters per second, by time, which is second. So it's meters per second, which mathematically equals the same thing as meters per second squared. Okay, so that's basically it for our notes. Now I've got some practice problems here that I want you to try on your own. So what I'm going to do is I'll just spend a couple seconds being on the practice problem page itself, in which you can pause, and then I will move to the next page, which will show the answer. So if you're struggling, you can follow along with the answer, okay? I'll move to the next page now. There you go. You can pause and you can follow along with what I did there. Let's move to the next one. We'll run a model rocket. Starts from the ground, reaches an upward velocity of 66 meters per second in 5 seconds. What was the acceleration? Pause if you need to. I'm going to move on. So Vf is 66, Vi is 0, delta T is 5. That means that we're going to end up doing 66 minus 0 divided by 5, 13.2 meters per second squared. Let's do a couple more. Pause here if you need to. And I'm moving on. There's your answer. So pretty much so far, they've all had minus a 0, right? An initial velocity of 0. This next one is different. Pause here if you need to. Notice that it starts at 14 and ends up at 28. So you've got not an initial velocity of 0. Your initial velocity can be 14. So 28 minus 14 divided by 5.5. And there's your answer. One last question after this. This is a tough one. Okay, and because we're not in class, I will not expect you to kind of know how to do a question like this on your own right away. Give it a shot, but this one involves a change in direction. So read this. You can pause it. You can try I will explain how to get the answer on the next slide. So a professional baseball pitcher pitches a ball given at a velocity of 45 meters per second towards the batter. Batted ball has a velocity of 30 meters per second back towards the pitcher. Let the direction from the batter to the pitcher be the positive direction. That means that if the change of velocity takes place over 1.2 seconds, what was the acceleration of the baseball? So here is the key thing to this one, is if the direction from the batter to the pitcher is positive, that means that our final velocity is positive 30. But that means that the ball that was thrown from the pitcher to the batter, if that's the negative direction, then that means that our initial velocity was not 45, it was negative 45. Now, if you know that, everything just works out the same. But what you'll see here is a double negative. So you have VF minus VI, so that's 30 minus 45, which gives you a positive 75 divided by 1.2 is 62.5 meters per second. So, wow, great work. We got through a lot there. It's good. If you're not understanding all of it, there's actually a lot of practice problems that you can work on, and I'm going to get you to work on tomorrow as well in your notebooklets. So good luck with that. Just email me if you have questions, and please just remember, just try to keep it up if you can. We are now in the home stretch. We'll try to get as we can. So have a great day, and yeah, I'll be in contact with you all tomorrow.